So thank you very much for the invitation. It's a great pleasure to be back in Cambridge. So I'm going to talk about an ongoing joint work with Jérémy Bettinelli, and the goal of this work essentially is to generalize the result of convergence of uniform random maps of the sphere to the Brownian map to more general surfaces, okay, or at least compact surfaces. So let me start with an introduction. So, okay, so as you know, or as you probably know, I'm going to go pretty quickly through the definitions, but okay, a map, okay, is an embedding of a graph, so really a finite graph, so in a surface, in such a way that all faces, so which are the connected components of the complement of the embedding, are topological polygons, or let's say are homeomorphic to disks. Okay, so in fact, as long as you are interested only in the case where the surface in question is the sphere, so in the case of S2, it's really just the same to just consider, so maybe I'll use another color, it's really just the same to say that you consider an embedding of a finite, so I should say maybe, so here in this definition you don't need to specify that the graph is connected. It really comes as a consequence of the definition. In the case of the sphere, it is just equivalent to say that a map is, so on the sphere, S2, this is equivalent to saying that it is an embedding of a finite connected graph. And maybe here I can be more specific about what embedding means. It really means that the edges are not allowed to cross. Okay, this is not allowed. So really, if you want to add this edge, you really should add a vertex in the middle. Okay. So in fact, in the case of the sphere, by sending, say, one of the points of the sphere not on the embedding to infinity, it's really just the same not to draw the sphere and just to draw a finite graph in the plane. Okay, so that's really equivalent. However, for more general surfaces, this is really not, I mean, this embedding of a finite connected graph is not the proper definition. And a way to see that, maybe the simplest case, is to consider the case where the surface is a torus, and consider, for instance, the map which is made of a single vertex. Okay. Well, in that case, clearly, it's an embedding of a very simple finite connected graph. Okay. However, you see that the connected component, the connected components of the complement of the embedding in that case is just a torus minus 1 point, and this does not have the topology of a disk. Okay. There are non-contractible loops in this surface. Okay. So this is really not a map. Okay, it really should be somehow faithful to the topology of the surface it is embedded into. Okay, so another way to say it is that a map is a decomposition of a surface into polygons. Okay, so for instance, you can enrich maybe this graph in order to make it a map. You see that here, this map is really what you get when you glue together the opposite sides of a topological square. Okay, it's really the usual representation of the torus. Okay. Okay, so now what we want to do is to consider maps chosen at random in some way. And in order to do that, so maybe it will not be very surprising for those of you who are familiar with this topic, it's often very easy to consider the class of quadrangulations. Let's say that in many respects, it's the simplest from a combinatorial point of view. So we say that so a quadrangulation is a map whose faces all have degree 4. Okay, and here I'm going to enrich a little bit this picture by considering quadrangulations with boundaries. So quadrangulation with boundaries. So a map M is a quadrangulation with a boundary if all faces have degree 4, with the exception of maybe a finite number of marked faces of arbitrary degrees. Okay, so in this definition, of course, it's natural to view those really as quadrangulations, maybe of surfaces with boundaries, but there is a little, a little subtlety to it, which is that, okay, maybe I should say that, so again, all the faces have degree 4, so maybe this is a quadrangulation with a boundary. Okay, you have all faces of degree 4 except maybe the exterior face, which has degree 1, 2, 3, 4, 5, 6. Okay, but and this is a quadrangulation of a disk. Okay, the topological surface that is naturally associated to it is this disk. Okay, but you should be aware of the fact that this also counts as a quadrangulation with boundary. Okay, in other words, you see the face which the only face which is not of degree 4 in this map does not have a simple boundary, and it does not have to. Okay, so it's of course, what I'm going to say, this is more maybe a technical annoyance than a really substantial thing, but still for the results that I want to state, this is really the definition we use. Okay, so for instance, it could be even worse. Of course, you could have some little tree components here, and that would just be fine. Okay, this is still the exterior face here is still homeomorphic to a disk. Okay. Okay, so now we have the case of quadrangulation of S2. So maybe I'm going to use a definition. So let G be a number bigger than 0, and let's say sigma n to be, say, sigma n1, sigma n2, sigma n k, the sequence of integers for k. Well, that's actually yeah, that's right, nk for k greater than or equal to 0, and define q n g sigma n to be the set of quadrangulation, or let's say, yeah, that's fine, quadrangulations of the surface of genus G with k boundary faces of degrees sigma n1, sigma nk. Okay? And in fact, I want to add two more words to this definition. So I want to ask that the quadrangulations are also bipartite. And in fact, so therefore the degrees will be even. So I want to double all these quantities. And I want also the quadrangulation to be rooted. So, okay, so what does that mean? So bipartite means that there exists a bicoloration of the vertices. And by bicoloration, I mean that neighboring vertices must have different colors. Okay, so you can color the vertices in black and white in such a way that white vertices are only neighbors of black vertices and vice versa. Okay. And rooted just means that I've distinguished one of the edges and given it an orientation, and I call it the root of the map. Okay, so routing maps is a useful way to somehow kill the symmetries of the maps. It's always nicer to consider families of rooted maps. So here, okay, maybe the last thing I need to define here is the surface of genus G. Okay, so the surface of genus G just means that you consider the connected sum of G different tori. Okay, so you just consider a surface with G handles. Okay. And by the way, so the fact that the map is bipartite implies that there cannot be cycles with odd length. Okay. So in particular, it means that the boundary of the faces all the faces must have even degrees. In fact, in the planar case, it's also equivalent. As soon as you have a map in which all the faces have even degrees, then it's bipartite. But for general G, it's not the case. And a simple example is given by the map I've drawn in red here. It has a single vertex which is connected to itself, so it cannot have a bicoloration, even though it is made of only one square. Okay. Certainly has an even degree. Okay. Okay, so now let's discuss the case of S2, which is the case where G is equal to K is equal to 0. So I consider a map on S2 with no distinguished boundary faces. Okay. And so let Qn be a uniform random variable in the set Qn 0 and with no boundary component. Yes. Oh yeah, sure, of course. Thank you. Quadrangulation and with n squares. Thank you. And by square, of course, the distinguished faces could be squares as well, but when I talk about a square, I really mean a non-distinguished square. Okay. Thank you. Okay, so let Qn be a uniform random variable in the set of quadrangulations with n squares that are rooted and on the sphere. And so we want to consider scaling limits of Qn. And in order to do that, we want to view Qn as a metric space. Okay? That is, we want to embed the set of vertices of Qn with the graph distance dQn. And by graph distance, okay, it's of course the distance between two vertices is the minimal number of edges that you need to cross to go from the first vertex to the second one. And here I want to mention that in principle it would be possible to consider other distances on the maps. There are of course many other instances of natural distances that you can define on the set of vertices, or even on the surface itself, based on the structure of the map. And it is expected that the results that I'm discussing here do not actually depend on the details of the choice of this distance. Okay, it just turns out that the graph distance has nice combinatorial properties. Now what you want to do, of course, is as the number of squares go to infinity, the size of the map grows as well. So you want to rescale the graph distance in order to keep it compact somehow. And it turns out that the proper renormalization, so there is a scaling constant that we usually add for reasons that will become clearer later. So the important thing, of course, is that you rescale distances by n to the power 1/4. Then there is this scaling constant 9/8. Then this converges in distribution as n goes to infinity. So it's a random metric space to some limit SD, which is called the Brownian map. Okay, and this convergence holds in the so-called Gromov-Hausdorff topology. So maybe I should say, for those of you who see that for the first time, that a sequence of metric spaces xn dn, so compact metric spaces, converge for the Gromov-Hausdorff topology to a limit xd, if and only if there exists a metric space zd, so maybe a compact metric space, and x prime n, d prime n, x prime, d prime isometric copies of xn, dn, and xd in z. So maybe here I should say that these distances d prime n are really restrictions of the distance delta to these sets x prime n and x prime, such that the Hausdorff distance between x prime n and x prime goes to 0 as n goes to infinity. Okay, so maybe I should draw a little picture here. So if you have two abstractly defined compact metric spaces, you will say that those are closed if you can embed both of them in some certainly bigger space Z delta. So you have two subsets, x prime n and should maybe use another color, x prime n and maybe something like this, x prime, in such a way that the Hausdorff distance between these two sets, so in this case maybe it's achieved by this distance, is small. Okay? So it's a way to compare two abstract, compact metric spaces, and it does say endow the space of metric spaces seen up to isometry with a nice topology in which you can consider, for instance, convergence in distribution and random variables. Okay. Okay, so this result is as a history dating back to a paper by Chassin and Schaeffer in 2004, where they proved that certain functionals of this space converge, to some limiting random variables, and then there was, they asked in their paper whether such a convergence was holding. It was, of course, a natural thing to conjecture, and then there were some important papers proving gradually this conjecture, in particular by Le Gall, who showed that up to extraction you had indeed Gromov-Hausdorff subsequential limits, okay? And then there was the question of uniqueness of the limiting space, which was solved in independent papers by Jean-François Le Gall and myself about 4 years ago. Okay. So now what I want to do is to use this result as a basis to, more general surfaces. Okay. And so the result is the following. So let sigma n and sigma n1, sigma nk be a sequence of integers for some k. So I still want to allow k to be possibly 0, okay, and g be fixed, and let qn be a uniform random variable in the set of quadrangulations, so with n squares, with boundary components of sizes sigma n1, or actually 2 sigma n1, 2 sigma nk, and in genus G. Okay. Then, if you consider the set of vertices of Qn and rescale again the graph distance by 9/8 n to the 1/4, then this converges in distribution as n goes to infinity to some limiting space that maybe you want to call S sigma G D, as soon as sigma n over square root 2n. Okay, so maybe I should have said that before, but so somehow the volume of the map is always the same. You want to parameterize the volume by the number of squares, okay? But the thing is also you should control the sizes of the boundaries, okay? And in order to see something non-trivial in the limit, it turns out that the proper scaling of the boundary size is much bigger than the typical distance. It's not n to the 1/4, but rather the square of this typical distance. And so you want sigma n over square root 2n to converge as n goes to infinity to some limit sigma in 0 infinity to the power k. And of course, in the Gromov-Hausdorff topology. Okay. So of course, you could ask what is happening when you don't have this convergence, and in particular when sigma n over square root 2n, some of the components are allowed to be 0, and in this case, these components will just disappear. Okay, if it turns out that some sigma ni is a little o of square root n, then it implies that the same result, if you like, but you just remove the ith coordinate in the right-hand side. Okay, and in the case where one of these sigmas is really bigger than square root 2n, then something completely different happens, and somehow the boundary takes over. Okay, and what you see is not really something looking like a map or a surface anymore, but rather a random tree. Okay, so I don't want to discuss that here. And moreover, so the topology of S sigma G is almost surely the same as a surface with G handles and with K boundary components. Okay, so in this case, K is equal to 4 and G is equal to 3. Okay, So there is something important that should be noted at this point, which is that even though the maps that we've been considering are not stricto sensu maps of this surface, okay, which is a decomposition of this surface into squares. So even though this is not the case, these problems here, the fact that the boundary components may have separating vertices, it completely disappears in the limit. Okay, in the limit, you do get something which is homeomorphic to this surface, and of course, it is natural to expect that the same holds if the boundary components, I mean the boundary faces, are simple. Or let's say have simple boundary. Okay, but this is okay. This is somehow more technical for various reasons. Okay, maybe another thing that I should comment is also that, so almost surely it holds that the Hausdorff dimension of S sigma G is equal to 4, and if sigma is not the empty sequence, then the Hausdorff dimension of S of the boundary of SG sigma, in fact of all the boundary components of SG sigma, is equal to 2, almost surely. Okay, so of course, okay, this result for G sigma is equal to 0, was Le Gall, 2007, I think, and in fact, in this generality, there is a paper by Bettinelli in the general case. So actually, maybe I should have said that before, but so a recent study by Bettinelli shows the existence of such scaling limits, okay, under the same assumptions, but again, only up to extraction, okay? So shows existence of scaling limits up to extraction. Okay, so the goal of this work is to lift this up to extraction statement.
What is the role of these numbers sigma in the limit?
That's right. So if you like this sigma, so in this picture, of course, the different components, I mean the different boundary components play the same role. Okay, if you see the surface as being a topological surface. However, what you should think is that this SG sigma is a random surface in which the boundary components have different sizes. Okay, and these sigmas, they somehow measure the sizes of these different boundary components.
They're all homeomorphic.
Yes, if you like, I mean they are all homomorphic to circles. Okay, as topological objects, they are just circles drawn on a surface. Okay, but as in the metric sense, if you like, they have different sizes. So, for instance, a way to view that would be maybe to measure these with Hausdorff measures with a proper gauge function. Okay, and this is not at all something that is known at the moment, but it's natural to think that these quantities are Hausdorff measures for some gauge function close to R squared. Okay, because of this here. Actually, you can. Well, you can also approach this measure by taking little neighborhoods. You take, if you like, epsilon neighborhoods. You look at the measure and you rescale it in a proper way. Then you will have convergence in probability, or okay, not entirely sure about that, but you will have some kind of convergence to this sigma. You can. Yes. I mean, you can see it from the construction, if you like, but which I'm going to explain course, here it's not possible to read it from the statement, right? It comes from the construction. Okay. So in fact, so I want to comment a little bit on how we want to prove such a result. And there are really two different steps in order to do that. So two steps are needed. Well, actually, really three steps. The first step is the convergence to the Brownian map here. Okay, and the second step is the case of the disk, which is g equal to 0 and sigma well, is equal to just a singleton sigma 1, say. Okay. And then once you have shown this result for the disk, somehow you have the necessary ingredients to build this surface here by surgical operation. So use the Brownian map. So let's say the Brownian sphere and the Brownian disk as building pieces, or maybe building blocks, for SG, for the general SG sigma. Okay, and okay. So in the remaining time, what I want to do is to explain some of the ideas, some of the key ideas of both these steps. So again, okay, something that I should have maybe commented on, but this result for the topology. So in the case of the Brownian sphere, so this was a result by Le Gall and Paulin, and also in this generality, it's also a part of this paper by Bettinelli. Actually, what he shows is that all possible subsequential limits to extraction will have this topology. The thing is that with this strategy of proof, we can also reprove, in fact, these results. I hope to make it clearer at the end of the talk. Okay. So before I discuss the case of the disk, maybe I need to recall some important aspects of the construction of the Brownian map. I'm going to be a little quick here, so so the key fact is that quadrangulations, so of the sphere, so can be encoded by a natural family of labeled trees, and really the construction of the Brownian map is a continuum analog of this encoding. Okay, so this encoding is called the Corey-Vauquelin-Schaeffer bijection. So which was found in the early 80s by Corey-Vauquelin, and which was more or less abandoned until Schaeffer really developed the ideas of bijective enumerations of maps, starting with his PhD in the late 90s. So okay, so again, I'm not going to give the full details of the construction. I'm sure that many of you have seen that at least once. So the trees that I'm considering are just plain trees or rooted plain trees, which are also labeled. So every vertex carries a label. And when you go from one vertex to a neighbor, you are allowed to add 1, to subtract 1, or to do nothing. Okay, so for instance, this one could be 0, this one can be 1, this one can be 2, and this one can be 0, for instance. Okay, so this is an allowed label tree. Okay? And then what you do is, starting from this tree, you build a map by adding extra arcs to this, or extra edges. What you do is, every time you encounter a corner of the tree, you want to link this corner by an arc to the next available corner of smaller label. Okay, so for instance, this one had label 0. You want to link it to the first available corner with label 0 minus 1. Okay? And you do it for all the corners of the tree. So this 0 would be also linked to this minus 1, this one to this 0, and so on. Okay, so I'm not going to draw all the edges, but this is really the construction. And when you are done, in fact, you end up with a quadrangulation. So I should also mention that if you have a vertex of label which is the overall minimum, then in this case you should connect it to an extra sink, if you like, with the label what it should be, namely the minimum label minus 1. Okay? Okay, so from a label tree, you get a quadrangulation. So it's a quadrangulation, so it has n edges. You end up with a quadrangulation with n faces. And in fact, from the construction, it's rather clear that you have a vertex which is also distinguished, which is usually called V star. So plus a distinguished vertex. Okay, but you can, if you are interested only in sampling the map, you can just forget this distinguished vertex. Okay, and you just, if you start with a uniform label tree with n edges, you end up with a uniform quadrangulation with n faces. Okay. Now, so this allows you to go from trees to quadrangulations, and in order to take scaling limits, what you can do is you can first take a scaling limit of the left-hand side. And a nice way to do it is to see a uniform tree with n edges as being coded by an excursion of a simple random walk. So maybe I should draw the actual random walk encoding this tree here. So you can code a uniform tree with n edges with an excursion of a simple random walk of length 2n. Okay, in a quite natural way. You imagine a particle that goes around the tree at speed 1, and at time t, you just record the height of this particle in the tree. It's very easy to see that you can pass from this excursion to the tree, and you can also record the positions of the labels at the same time. So you start from 0. Go to minus 1, then back to 0, 0, 1, 0, 1, and so on. So you have the contour, it's called the contour of Tn, and the label process of Tn. Okay. So I had 0, I guess, 1, 0, minus 1, 0, 0. Okay, so now, so it's quite common fact is that if you rescale, so let me call this contour process Cn and this label process Ln. So if you rescale the contour process Cn in a diffusive fashion, so you rescale the time parameter by 2n in order to bring this back into the interval 0, 1, and the space by square root of 2n, then this converges in distribution to a process E, which is a normalized Brownian excursion. And the label process, well, you should also rescale the time parameter by 2n. But now, what you should be aware of is that this label process describes really a random walk indexed by the branches of the tree. Okay, so if you consider maybe one of the times here, then what you see here is a random walk with a length which is given by Cn at time 2nt. Okay, so therefore this height is typically of order square root 2n, but the variance of the walk that you observe here is really the variance of a uniform random walk with steps in this uniformly distributed in this set of 3 elements. Okay, and the variance in this case is equal to 2/3, and that explains that you should, well, after some computations, that explains why you should first of all rescale by the square root of 2n. Okay, so you get a first 2n to the power 1/4, and then you get an extra 4/9 to the power 1/4, which corresponds to the variance 2/3. It's really the standard deviation corresponding to this variance. Okay? So once you have done that, it is clear that the labels along the tree should converge to standard Brownian motions indexed by somehow by the branches of the tree. So you get a convergence to Ez, where E is the normalized Brownian excursion, and Z should be understood as Brownian motion. So indexed by E. So at this moment, it's maybe not so clear what it means to be indexed by E. But then what you can do is you can in turn interpret E as coding a random continuum tree which is usually called the Brownian tree and denoted by TE. And this tree, you should interpret it as a random metric space whose contour process is given by E. So I'm not going to be more specific about this because it would take too much time. And with this interpretation of E encoding a tree, then Z is simply Brownian motion indexed by this tree TE. Okay, and starting at 0, maybe at the root. Okay, so along each of the branches of the tree, you have Brownian motion started at this point. Okay, and if you go to a different branch, then the increments of these different Brownian motions are independent. Okay, now, so what we have is from a label tree, can construct a quadrangulation. And we know that label tree rescaled converge to the Brownian CRT plus Brownian motion indexed by it. And what we want to do is to construct the analog of this arrow in the discrete world, okay, and construct the Brownian map. So I'm not going to be extremely specific about it, but I just want to convey an important idea, which is the following. So in the construction of the quadrangulation from the tree, what you have to do is to add certain arcs of length 1. Okay, so maybe this is also something that I should have discussed before, but of course, you know, these green edges are edges of the quadrangulation, so you should think about all of them to be of length 1. And there is another important thing, which is that from the fact that all the all the green edges link two vertices whose labels differ by 1, well, it is also clear that if you consider, the chain of arcs going from any vertex to its consecutive successors, so from 0 to -1 and -1 to -2 in this way, or maybe from 2 to 1 to 0 to -1 to -2, then all these paths are really shortest paths to V star. Okay, you cannot go faster than decreasing by 1 at every step. Okay, so all these paths are really shortest paths to V star. They are geodesic paths. So this is an important. These are two important ideas. Sorry. So the first is that you should really link two vertices in the tree which have, well, the same label, or maybe L and L-1, and such that this L-1 is the first you encounter, so that all the labels in between, when you do the contour, all the labels in between are bigger than L. So that's the first idea. And the second idea is that if you continue drawing these arcs, okay, so L-2, L-3, and so on, until you meet the vertex of smaller label, so this is smallest L, then what you have done is you have constructed a geodesic path in the map from this vertex to V star. Okay? And these two ideas, they generalize very nicely, in fact, in the continuum picture. So, of course, in the continuum picture, what happens is that this distinction between L and L-1 must disappear because you have rescaled all the labels by n to the 1/4. Okay? So in the continuum picture, what you should do is you should draw an arc of length, of vanishing length. Okay? So namely, you should identify. So you should identify two vertices A and B in the tree TE, such that the label of the vertex A is equal to the label of the vertex B, where Z is this label function that you can either define on 0, 1 or on the Brownian tree itself, and such that Z of C is greater than or equal to Z of A in the contour interval between A and B. Okay, so you should really identify two vertices. So here A is here and B is there, and all the vertices in the contour interval here are bigger than Z of A, which is equal to Z of B. Okay. Now, you should be a little bit careful with this definition, because here it seems that I'm going from A to B. Okay, but you really have two contour, or at least two contour intervals between two vertices. It could also be the case that on the contour interval from B to A on the other side, the same property happens. Okay, both are possible. It's possible that you identify vertices by going somehow around the root of the tree. Okay, you don't necessarily have to go from the left vertices to the first encountered vertex to the second one. So that's the first thing. And the second thing is that the path from a vertex A in TE visiting the vertices that achieve new minima, say to the right of A, is a geodesic in the Brownian map from A to A star which achieves the overall minimum of Z. Okay, so it's a rather convoluted sentence, but what it really means is that you start from A and you look at the first vertex in the tree that arrives to the right of A, so after in the contour order, and which has a label, say ZA minus some R for some fixed R. And what you can do now is to consider the path which visits exactly these vertices. Okay, so it will be a path somehow which goes from left to right until it visits the vertex with overall minimum label, A star. Okay, then this path is a continuous path and is a geodesic in the Brownian map. Okay. Okay. Now I want to change a little bit this view on the Brownian map by asking what happens if we actually disallow these if we actually disallow the identifications that actually go around the root. Okay, so you start from a label tree. Okay, and let me say, for instance, that the vertex of minimum label is here at the top. Okay, and then you have here a vertex of label 0. Then, as we know, we have a first geodesic going from 0 to A star. Okay, so this is maybe this geodesic. It visits again the first record. So this is, for instance, the first time at label minus R. Okay, for some R. Okay, so we have a first geodesic to A star. And now you should be aware that in the Brownian map, if you consider also the first time at minus R, but going to the right now, okay, so this is also the first time at minus R, then really these 2 points are the same in the Brownian map, okay, because by definition they have the same label, they are both minus R, and in between all the labels are bigger by definition. Okay, so this should really be identified, which means that you have somehow a distinguished geodesic from 0 to A star, which is somehow doubled. Yeah, you really have two of them, coding, of course, the same thing. So what you do if you disallow these identifications, so disallowing identifications, so let me call that maybe gamma right, let's say D of R, and this is gamma G of R. So disallowing the identifications of gamma D R and gamma G R opens the distinguished geodesic from the root to A star in the Brownian map. Okay, so in pictures, imagine that again the Brownian map is a random sphere that is obtained by taking this quotient of the Brownian tree. Okay, so you should imagine it as a random sphere, and in this random sphere you have a distinguished pair of points, which is the point visited at time 0 in the description of the tree, and the point achieving the overall minimum. And you have a distinguished geodesic between these 2 points. And in this coding, this geodesic is really doubled. Okay, you have somehow the red part and the green part here. Okay. So what you do by disallowing this identification is really that you cut open this map into so what is called a map. So maybe this is the map here. Now this is here. You get a map with geodesic boundaries. It's also called a slice. So it has been introduced in various guises. So by Le Gall in his paper on the uniqueness of the Brownian map. And the slices, or at least discrete slices, had been introduced by Boutier and Guiter around the same time. Okay, so in the end, what you get is a label tree. Well, okay, labeled CRT or a label tree. You can view it in two ways. It's either a Brownian map with some decorations. Okay, you can, for instance, forget the role of 0 and A star, and you just get the Brownian map. But you can also view it as a map with two geodesic boundaries. Okay, so by this, I mean that this is an object which is homeomorphic to a disk, in which this part of the boundary, the green part and the red part, are geodesics with the same length. Okay. Okay. Now from this, I want to explain. So I'm already late because I started early, but but at least I want to arrive at some punchline. Okay, so I want to discuss the case of the disk. And so the case of the disk, first of all, you need to generalize the coding by the Corey-Vauquelin-Schaeffer bijection. Now you can use a coding of elements of quadrangulations in genus 0 with a single boundary component, maybe n sigma, by what is called the Boutier, Di Francesco, and Guiter bijection, which I want to explain really in a nutshell. What you do is you consider a cycle okay, a cycle with sigma vertices. Okay, so soon sigma will be sigma n, okay, which is equivalent to some limiting quantity sigma square root of 2n. But for now, I want to ignore this point. And you label it in a uniform way by taking, so you label these cycles by vertices, say L and L prime, in such a way that L prime minus L is always an integer bigger than -1. Okay, so you can have arbitrary positive jumps between consecutive vertices, but you cannot decrease by more than 1. And then on top of that, you put a label tree in the same sense as before on each of those vertices. Okay, so you have label trees. So what you get is, if you like, a labeled forest, so ordered in a cyclic way, with a total of n, well, really n plus sigma edges. So you have the sigma edges of the floor of the forest, okay? And then you have a total of n edges in all these trees, okay? And how does it work, the bijection? Well, you should again remember that these trees are labeled, so they bear labels, say L. And in order to build a quadrangulation with a boundary, you do the exact same construction as before. Namely, you go around the face defining this forest, and you link every vertex with the successor, the next available vertex of label smaller, which is smaller. Okay? You continue like that until you find the smaller available vertex, which you connect to a distinguished vertex. So it's the exact same construction. Same as Corey-Vauquelin-Schaeffer bijection. Now, in order to take scaling limits, there is a natural route, which is to consider individually the scaling limits of all these trees. Okay? And if you have a forest like this, rather than an excursion of a walk, it is natural to code these trees by a walk which, after it finishes visiting one of the trees of the forest, maybe this one, does a minus jump here and starts exploring the next tree of the forest and so on. Okay? So what happens is that in the end, it will visit for the first time the level minus sigma at time, I guess 2n plus sigma, okay, which is the number of edges that you visit in the forest, times 2 because you visit every edge twice, plus sigma, the number of floor edges. And what happens is that this kind of first passage is called a first passage bridge of a random walk, will converge in the end to a Brownian motion conditioned to hit level minus sigma at time 1. And each of the excursions of this Brownian motion above its path minimum codes a single tree. Now, okay, so now what happens is that the scaling limit is a forest of labeled Brownian trees, which you can represent in the following way. So first of all, you have the labels of the floor, which of course has to rescale to a Brownian bridge because it's an excursion, if you like, it's a random walk, which is a condition to cycle on itself. Okay, so you have a Brownian bridge. And on top of that, you have a kind of Poisson process of, given by the excursions of Brownian motion above its infimum, you have a kind of Poisson process of trees, which I want to represent in this way upside down, plus a Poisson, it's really a conditioned Poisson process of labeled Brownian trees. Okay, so you should be aware of two things here. The first is that the nature of the spatial displacement here is different from the spatial displacement in the trees, which was this +1, -1, or 0. And this results in an extra factor, scaling factor for this Brownian bridge, which has actually important consequences, which I don't have time to discuss here. Now, the idea is that each of these trees, as we know, encodes a map with a geodesic boundary. Okay? So in order to build the Brownian disk out of this forest, well, as we said, we perform the Corey-Vauquelin-Schaeffer bijection within each of these trees. But what we do then is we glue these boundaries to the next available free boundary that is facing it. Okay. So what we do is we glue a forest or glue a collection of maps with geodesic boundaries. Okay, so in order to conclude, just need two comments here. So you know, in the end, what you get is that the Brownian disk, you view it really as a collection of slices that are glued together. Okay, so something maybe like this, then something like that, and so on and so forth. But there are now two important difficulties. The first one is that there are, of course, infinitely many slices. Okay, so it is not clear in the end that this gluing operation is well defined, and this in two respects. Well, first of all, it's not clear that every point of a green boundary is indeed connected to someone else. It would be, in principle, possible that there is some little part which is lost here and which is not connected to any other, okay, because it's blocked maybe by the excursion. And that would be bad, of course, because it would mean that somewhere you have a part which is completely disconnected. Okay, and you don't want that. You want the result to be a disk. But this we know that it does not happen. It's a result that dates back to the thesis of Bettinelli. But still, you still have an infinite number of them that accumulate. Okay? But the important thing here is that these species accumulate only near the boundary. Okay? And you can check, so it's, I don't have time to discuss that, but you can check that for most points, a geodesic between these 2 points will visit only a finite number of such slices. Therefore, if you want to understand the distances within these Brownian disks, you only need to understand the distances in spaces that are made by gluing a finite, arbitrarily large but finite number of such slices. And it holds in a very strong sense. It means that for a typical pair of points, it is possible to find an integer n such that by gluing, say, the n largest slices here, you obtain already the exact distance between these 2 points. So this is really something that is stationary. Okay, so I'm already very late, so I didn't have time to discuss the more general case. So the idea, just to conclude, is that the ideas that are involved for the general case are in fact quite different from those ones. You also do a kind of construction of the general spaces by a gluing of spaces, but of Brownian-like maps with geodesic boundaries. But the thing is that you only glue a finite number of them, not an infinite one. Somehow, when you have the Brownian map and the Brownian disk, you have everything that you need to construct the general SG sigma. And as you can guess, the boundary components of SG sigma are made of little pieces of Brownian disks, while somehow the bulk components are made of little pieces of Brownian maps. But I really don't have time to discuss that. So thanks for your attention.
So are there any questions for Gregory?
So, when you're constructing a disk out of spheres, in my naive sense, I would say take a sphere, cut out a piece, and then you have a disk. Isn't there a different way to get to
Well, yeah, that's a good question. So first of all, I'm not really constructing a disk out of a sphere, right? And okay, strictly speaking, I'm constructing it out of little disks. Okay, but of course, it would be very natural also to say, well, after all, I can just take, for instance, the Brownian map, take out a ball of radius r, and look at one of the connected components of the complement, and that indeed would be another. Of course, you have to be careful, because in that case the size will be random itself. Okay, so you can condition maybe the size to be equal to 1, and condition also on the size of the boundary. And indeed, if you do that in a proper way, you will also get these spaces. But it's not obvious in itself. Well, I don't think, for instance, it is a natural way to get, maybe it's a way to get a convergence of disks in which you don't fix either the volume of the perimeter. This sounds reasonable. However, I don't think you can get easily a condition result like that from this construction. But you are making a good point, of course. Yes.
Is it to see that the geodesic between two interior points does not hit the boundary of the disk?
So, well, it's also a kind of rerouting trick in the same rerouting argument. So you see, in this case, what you get is that all these paths, these green and red paths, they are geodesics aiming to a distinguished vertex V star, okay, which is itself uniform. So what you get is that from, let's say, from any boundary component, it's not really important to take a boundary component, but just for visualizing, you can show that once you've left this boundary component, you will never hit it again. And it, in fact, comes from the fact that every point on a green component is mated to a point on the corresponding red component. Okay, so somehow you see that at least these geodesics to V star, once they leave the boundary, they never encounter it again. Okay, so it's natural to think that for other vertices, maybe you will hit the boundary once, but after that, never again, and that for typical vertices, you will not actually hit the boundary. Well, in fact, okay, you can in fact also take any vertex inside one of these slices, and then you know exactly what the geodesics are. Okay, these slices are coded by little Brownian trees. You can consider the successors. You can check that you will never hit the boundary. So at least for vertices aiming to V star, you don't hit the boundary, or except maybe at the start. And then V star is uniform. So it means that for two typical vertices, you will not hit the boundary. And as soon as you show that these slices accumulate only near the boundary, then you are done.
So can you say a bit what is the distinction between what you were talking about in the non-orientable case that makes it more difficult?
But the non-orientable case is Jérémy's business. So you can ask Jérémy. Yeah. So these compact Brownian surfaces, of course, I should have said maybe oriented compact surfaces, but there is also a non-orientable side to it. And it's actually a project by Jérémy and Maciek Dolega and Guillaume Chapuis to perform similar arguments of the kinds of those that I didn't have time to present for non-orientable surfaces. The problem, well, it's quite obvious what kind of problem occurs. Namely, you see that there is a convention in the Corriveau-Klein-Schaeffer bijection, which is go from left to right or from right to left. And this disappears in the non-orientable case. So you have to make local choices, and that makes the study quite a lot more complicated. But fortunately enough, in the scaling limit, it seems, at least from my discussions with Jérémy, it seems that the picture looks exactly the same. Namely, if you want to construct the Brownian map, Brownian projective plane, essentially you take a slice and you glue it in a non-orientable way. So there is a kind of nice thing that seems to happen for non-orientable surfaces as well.
So do you have cutting and pasting result in this? I mean, in the scaling limit, like for Brownian thing? Can you maybe do you know how to reglue Brownian disks and spheres with boundary?
Yeah, that's the idea. I mean, so since I didn't have time at all to discuss that, maybe we can discuss that later. But the thing is that the way you construct these compact Brownian surfaces is really by cutting, say, avatars of Brownian surfaces, of Brownian maps. They are really conditioned versions in a slightly complicated way. So that's and you cut those along certain geodesics, and then you reglue them. Yeah, that's absolutely the way you do it. However, something that it's not something you really have to cut along a path that are nice, like geodesics. Otherwise, it's very difficult to glue two metric spaces along curves that are not, say, Lipschitz. And for instance, if you take two Brownian disks and glue the boundary together, so these are now very wild boundaries. They have Hausdorff dimension 2. You would expect to get some kind of map with a self-avoiding walk, but from the metric point of view, it's very difficult to define. And actually, there's a connection, of course, between this story and Jason and Scott's and Bertrand's papers on gluing of quantum surfaces. But somehow it's these are two kind of different stories. You have first of all a metric gluing, And then you have also this kind of conformal gluings which are somehow better behaved. Or so it seems.
Maybe we'll thank Grégory one more time.
Thank you.